Yeah, thank you, Sophie. I usually do this presentation in Australia, and I mainly get asked two questions. The first one is, why did James Cameron, a Canadian-born US filmmaker, choose me to do the design and development and also build the submersible, Deep Sea Challenger? And the second question is, why was it built in Australia and not in the US? Just quickly on my background, I'm a broadcast engineer by trade. Worked with the Australian Broadcasting Corporation for 25 years. Now, how does that lead me into building a submersible? Before I move to the next slide, I'll just explain a little bit about the sub to you. What we call the pressure vessel, the PVHO, the pressure vessel for human occupation, is in the lower part of the submersible, behind the acrylic viewport that you can see. This little device on the right-hand side is a manipulator that can extend and form the functions of an underwater manipulator. It can pick up rocks, it can do samples. So the intent of the machine was to do science. Behind this door is hydraulically opened, and that will reveal a science tray so samples can be placed. We also had core sampling, various other bits and pieces for science. The two arms, this one on the starboard side, has a 3D camera system. The arm can be articulated fore and aft. The arm on the opposite side has a spotlight at the end. There's about a 700 watt LED light. So both these arms can be moved forward, aft. Both have got pan and tilt functions, so they can do a lot of imaging. The rest of the sub is, there's a bank of LED arrays at the top, more arrays around the this brow piece, LEDs on the boom arm. There's also LEDs underneath the sub. Thruster motors, there are actually 6 motors on each side, so it's a total of 12 thruster motors for propulsion. The battery systems are in the side of a sub, and the bulk of this area up here is purely flotation and the structural strength of the sub. Just getting back to me, I may have been a broadcast engineer, but I was also a fairly avid caver when I left school, firstly through the Boy Scouts and then through some of the university clubs. And I learnt diving. I was very keen, very adept with being into the ocean. I lived and grew up in the eastern suburbs of Sydney, and spent more time down the beach than at home doing homework. This trip here was 1988, so some of the slides are a little bit dated. Lost a little bit of quality about them, but some of the caves of the Nullarbor Plain are absolutely immense. We actually decided on this particular occasion that we would invest in some good German technology, this Aquazep scooter. So we decided that we would do this cave diving expedition to this particular cave, Panican Plains, and we thought if we made a documentary film about it, we could get sponsorship money. So with the money, we end up buying a hell of a lot of dive equipment and got sponsorship for even more. So it was, it was in the year when that sort of thing could happen. We had money for doing this great adventure. From that expedition, incidentally, which ended in a near catastrophe in that the cave entrance collapsed with 13 of us inside. So, from all the newspaper reports, that we were all buried alive and we weren't going to get out, and it was quite dramatic at the time. But really, being in a situation, we had our own cave radios that I personally wound the coils myself. So we were able to communicate with the surface. We could understand the nature of this collapse. It was a big cyclonic storm, but it gave us a good lot of headlines and publicity for this, the release of really our first documentary film. I went on with a friend of mine, Andrew White, and we decided for the next 10 years that we would do documentary films, which took me around the world. And we went cave diving in lots of different places. We also dived with whale sharks off West Australia, great white sharks in southern Australia, crocodiles in Queensland. And then we went over to all the Bahamas, more cave diving, Galapagos, Alaska. We dived in ice caves and caving in glaciers, which was absolutely amazing. Yeah, in 2002, I was up in Kiel, Germany, and at this stage, Andrew had been headhunted by James Cameron. And Andrew was, my partner in, really I was working with Andrew. He was a producer for his documentary series. And when he was headhunted by James, the first expedition we did was a repeat of going to the Titanic. Neither of us had been there. It was our first deep sea expedition. And Andrew fell straight into place. He was James Cameron's producer. Andrew brought me on as his technical advisor. And we quickly learned to learn what the systems are on the sub, in particular the requirements for powerful lights, which were HMI type at the time. And also it was Jim's idea that he was going to trial his 3D camera for Avatar. Most people would do it in a studio, or if you're going to take it underwater, say at the Great Barrier Reef, but not James Cameron. He puts it on a mere submersible that's capable of 6,000 metres, and it goes back to Titanic, which is in about 3,500 metres. But he did admit on the very first dive of that expedition, that he got more footage from that very first dive than he did on all the dives he did when he was filming Titanic. So I ended up building up quite a rapport with James Cameron, and I was invited back on this expedition, which was to Expedition Bismarck. It was my first opportunity to dive in one of the Russian Mir submersibles. Mentioned 6,000 metre rated, and I couldn't have been happier. The descent took 3 hours. In the first 30 seconds, I had gone deeper than I'd ever scuba dived. I had done a couple of other smaller submersible dives, and they were just sort of over within minutes, and then we spent another best part of that 2.5, 3 hours in descent to 5,000 metres. And this is the bow of the Bismarck. With James Cameron, it's all about bringing back the images, and he has one Mir submersible with probably 8 by 1200 watt HMI lights. The other submersible has his 3D camera and of course some other lights, mainly on boom arms. The camera, he doesn't place the camera in the middle of the vehicle. He'll have it on one arm or out to one side, and the lights on the other side. So to James Cameron, it's all about lighting to get the shots. We started talking about Deep Sea Challenger when we were on that Bismarck expedition. In fact, we were coming back into the Azores before we went on and did some of the hydrothermal vents of the mid-Atlantic ridge. The area that we're looking at is this area in the black, the Mariana Trench. The water depth is nearly 11,000 metres. In fact, we have found spots now which exceed 11,000 metres, which is absolutely fantastic news for us. Moving on, just wanted to compare. We weren't the first to be there. It was done back in the 60s, and by a submersible called Trieste. It was actually Swiss technology, designed by Auguste Piccard, and he came up with this concept of literally a hot air balloon, but for underwater. In this case, the gondola is this metal sphere at the base of the vehicle, and the hull, which looks very much like a ship's hull, is full of aviation gasoline, which gives it the flotation that it needs. Unfortunately, back in the 60s, they had to do a lot of trial and error to work out the density changes of the fluids under pressure, the density changes with temperature, and they actually had to release quite an amount of gasoline to actually descend the sub through some of the thermoclines. So it was not really an environmentally friendly ship, and it's not the sort of vehicle we could build nowadays. Our vehicle on the right, it was actually designed so it had a weight limitation of about, we actually wanted it under 10 tonne, so we could take it on an expedition on any ship of opportunity. Most submersibles, I mentioned the Mir subs and the picture of them, they have a dedicated research vessel associated with them, and that costs a lot of money to operate a ship, as a lot of you might know. James Cameron didn't want a conventional submersible, so he didn't go to a submersible manufacturer. We'd already started to put electronics in oil and put them in plastic boxes or metal boxes with a diaphragm, so that the pressure could act on the liquid inside, and which meant that the electronics themselves would actually be subject to pressure. This limited the design of electronics somewhat. For a start, we couldn't use electrolytic capacitors that have a large airspace. Crystal oscillators, another example, and also a lot of opto-isolators. We came up with this concept of putting batteries, and this is a lithium polymer pack that I'm putting into a pressure vessel, which is 210 megapascal rated, roughly 30,000 pounds per square inch. And we also designed this injection moulded polycarbonate box for the battery pack. It was actually designed spring-loaded clips, a half O-ring seal in each side, but it would actually fit inside that pressure vessel so that we could develop the battery system. And again, as you can see, all the electronics flooded in oil. In fact, we ended up using a silicon fluid for the fluid. We do use coils, and coils have definitely been to the bottom of the Marianas Trench. We do have to use, when I was trialling a lot of commercially available products like DC-DC converters, power supplies, things like that, we found that some electronics work, some don't. At first we would just puncture the electrolytics and let them fill with oil. They work fine. But we also found with the magnetics that the permeability of a magnetic coil changes under pressure. So we had to use formers that had air spaces, and the designs of chokes and that would have to have an airspace. We also designed our own LED lighting. A lot of people use very high intensity LEDs, high power LEDs, and they have some sort of substrate on them, and they are affected by the oil, or in our case the silicon fluid, and they can often separate. I came up with a a backlighting style LED, which worked really well. And with the by using a large number of LEDs in a fairly small space, the added cooling of the assembly being fluid filled, we were operating and testing these down to 30,000 pounds per square inch, 207 MPa. We also did our own thruster motor development. We actually went for a frameless motor, but we also, wrong button. We also put our own driver electronics into the housing, which the entire motor assembly would be oil filled, and it would so the whole thing was operating at the full ocean depth pressure. Particularly with motor drivers, you need a lot of capacitance on the input rails, and we used, I've got an example here if anyone wants to come up later, but we used chip ceramic capacitors, banks of them, in replacement of electrolytic capacitors. That was just a bit of a close-up. Again, we end up using commercially available DC-DC converters, and usually the ones, as I said, that have an air gap in the cores would work fine at pressure. Some of the motors, we used a Parker Bayside. In fact, we had a bit of an issue. We didn't have the time to wait for the Parker Baysides. We had to go for Chinese motor, which we could get 2 weeks. And again, on the right, close-up of the DC-DC converter, the coil that was used. Moving on to getting away from coils. Our cameras, as mentioned, James Cameron, it's all about getting the shot. We actually developed our own, one of the issues with deep sea submersibles is that any airspace, if it collapses under pressure, will go off like a hand grenade. And if you've got a vessel here and one next to it, you could get a sympathetic implosion. And there are other types of buoyancy that use ceramic balls and that are hollow, very lightweight. But the risk is if one goes off, you might lose your entire flotation system. And again, we were quite concerned with cameras on this vessel. We're going to 11,000 meters, and if a camera casing was to implode, it might take out the other one. It could take out the main sphere that is occupied by the pilot. So we wanted to keep that space to the minimum volume. So I wrote a specification for the camera, and the electronics had to fit into a sphere that was no larger than a 25 millimeter diameter space. So it was a full HD SDI camera. It was limited. We had to have our gen lock between the two cameras for true stereo. But we came up with quite a neat little product. We also had to get fibre optic out of it, and we came up with our own solution to produce full ocean depth penetrators for fibre optic and electrical cables. Getting back to that human-occupied space, initially James Cameron wanted titanium, and I was working from Australia. We do a little bit of titanium, I guess, in our country, but Jim was pretty adamant. So I spent most of my nights working. I was on the phone to US sources, US companies, to forgers, welding, NDT. You name it, and I was just working myself stupid, I suppose. But when it came down to it, it was going to cost $2.5 million for US dollars for the titanium, and 2.5 years to get it. Anyway, I was on the phone one night, and someone said to me in the US, he said, "You've got to call Ross McNeil in Melbourne." And so I did, and the first words he said to me when I talked to him on the phone is, why titanium? There's stronger steels, stronger strength for weight steels than titanium. So the choice to me was pretty obvious. Jim didn't want the expense and he didn't want to spend that time waiting for raw material. So I went down, I was taking men to the local head press shop, which there is in Melbourne, and I was just shown a yard full of dies, and they said, well, what size do you want? And basically that's how we came up with the size of a submersible. We thought, that one. And give you some idea, when you're inside the submersible, if you're in a crouch position like that, the steel sphere is sort of, you barely have enough room to straighten your legs. James Cameron is another probably 150 millimetres taller than I am. So he was definitely unable to straighten his legs. So we ended up making the pressure vessel out of steel. And anyone worked in foundries or whatever, but there's a lot of heat involved. The sphere, which weighs 2.5 tonne, started off as two 7-tonne ingots of EN26 material. It was first forged into discs. Rather than pointing, I use a laser. It was then, that was machined, ultrasound tested, and then it was head pressed, so it's another heating process, and you get quite a bit of scale loss, as you can see these flakes of iron oxide scale coming off. The next process was to, after a certain amount of machining, was to weld the two spheres together, and finally the whole thing was put back in the oven again, further scale loss, and eventually oil quenched, and a lot of flames involved. We had the opportunity to do a laser scan of the sphere, so we had a true accurate model of the as-built. It did go out of round after the heat treating process by a factor of about 1 millimetre, but we were concerned. But what that gave us was a real model we could put back into FEA to prove the buckling factor. If you put a perfect model into a finite element analysis program, it probably won't fail by buckling because it's symmetrically perfect as you can get it. But anyway, we found that we were able to actually lighten the sphere after doing this final analysis, which was a bit of a godsend for us because we were getting quite heavy with the sub. And also we were able to run the program to get a 2.2 times operational load, which was a pretty good buckling factor for this pressure vessel. Proof of concept was that of the FEA was that we strain gauged the real sphere for when it went to Pennsylvania State University for pressure test. There are only 2 chambers that I could find worldwide that had a pressure vessel of 114 MPa. That was our working pressure, our design working pressure for the vessel. That was Pennsylvania State University. The other one was in Russia, and we had considered going to Russia for the testing. Being lowered into the 60-inch diameter, we're in the US now, so we're inches, 60-inch inside diameter chamber. And we were able to wire the strain gauges out through a data logger and recording the data inside the sphere, as well as monitoring during a pressure test. And our metallurgist, Ross McNeil, our design engineer for the sphere, Phil Durbin, and myself monitoring the strain gauging during pressure test. When it came time to float the sphere, do the rest of the sub-design, James Cameron wanted us to use syntactic foam for the structural member of a sub. And we did some basic analysis using FEA, but what we found was that the material was not homogeneous. It varied in density from top of a slab to the bottom of a slab. We also found it had poor tensile strength. I was liaising a lot with all the various syntactic foam manufacturers, and basically, when I'm talking syntactic foam, we're talking about hollow glass microspheres that are roughly 20 micron in diameter, or 20 to 50, maybe up to 200, and mixed in with an epoxy resin. So we end up coming up with our own production facility. Instead of mixing under vacuum like traditional manufacturers, we decided to mix it, then cure it, not mix it under a vacuum, but then we cure it in a hydroclave. So these pressure chambers are actually, the syntactic block goes into the chamber, it gets it gets filled with water, pressurized, it goes through a heat cycle to cure our foam. And it made it quite different to other commercially available foams. And we have since patented this technology. Our foam also varies from other conventional foams in that we were able to put an aramid pulp fibre into it, which really picked up tensile strength. Also, with our product, we can ultrasound it. With our hydroclave pressure, whatever air or gas is inside that block is sufficiently compressed to minimise any air void or volume, and it's making it such that we're able to ultrasound a 300 by 300, 1200 millimetre block of solid syntactic foam. The blocks are then machined and then assembled and glued into major assemblies. So this is a glue-up process for a number of blocks for a part of Deep Sea Challenger. The glued-up block is then machined. We actually had dye penetrate on this surface. We did have an issue, but we resolved what it was, and it just meant that particular piece was a little bit shorter than the rest of it. We just built it up with another piece. But we ended up machining quite complex shapes. You can see the join lines of the glue for each particular block, and this is one of the lowest sections of a sub. There were about 6 sections involved by the time we got the sub to full length. We also found that our product, because of the aramid pulp in it, really bonds well block to block, and it also takes a laminate really, really well. So, and this is unlike a lot of other syntactic foams. Just showing you the layup process. The first half is laminated. The whole unit was turned over, the other side, and finally the wrap and all the vacuum bagging for the process is taken away, and we end up with our syntactic beam. You can see the size of our sphere ready for fitting to the sub. This is our workshop in Leichhardt. The size of the sub, we're doing a bit more work on the back of it, so we just got a bit of a plastic cover just to keep the dust down in the workshop. And we've got a team down here looking at the webbing straps that we use to lift the sub. And also we use webbing, next shot will show you that. The sphere is actually restrained into the syntactic by webbing. We used polyester webbing. We found that we could tension it and stretch it, and even we did tests at pressure, and even when it's stretched, and even after it went diving, it would relax a bit, but it would still maintain a tension to hold that 2.5 tonne of sphere into its socket. So it wasn't going to go anywhere. It was quite, I don't know if anyone who tried to lift a big ball, but it's a nightmare to handle. You know, we made special harnesses and that. And of course, putting it in at that angle took quite a bit of ingenuity by the team. Okay, absolutely everything on the sub was pressure tested prior to going onto the sub. So that included all the thruster motors, battery assemblies, even the sonar devices that the off-the-shelf products, all our lighting, cameras, absolutely everything, and the syntactic foam went through the pressure chamber. Starting the assembly of one of the thruster modules, and that whole module, which would have the 6 thrusters, the 3 verticals being seen 1, 2 and 3, and the 3 horizontals are through this section here. The pigeonholes and each of these bays would contain 16 of our lithium polymer battery packs that would each slot in. And the idea of using syntactic pigeonholes was so that it would be a fire barrier. So if you had any issue with lithium polymer battery fire, hopefully it would be contained to one pack. We also had these fire irrigation hoses that would channel down to the back, and it would spray out water at the back and totally flood. Each of those hoses would flood 4 of those pigeonholes. So that was our fire protection scheme. Our lift points for the sub were literally these polyester straps, and we actually rated the lift point for the sub as 40 tonne, and that was to counter the 12 tonne static weight of the sub plus a little bit of dynamic conditions, from a sea state. So it had to be quite a heavily engineered lift point, and we did it with literally with syntactic foam, which is pretty much unheard of in any other submersible to date. We did use laminates or composites to that would clip over the syntactic beam. We wanted to keep the syntactic beam after it's laminated clear, so that if there were a crack or anything, we could it would be visible to the naked eye. Fortunately, no such incident occurred, or that we know of at this stage. The LED lights, you can see a whole just bank of LED lights, and all the wiring we place in what we call Tygon. It's a fuel and lubricant grade Tygon. It remains quite flexible, and that contains all our electrical wiring, and it's also fluid filled. Of course, when the sub went on to Deep Sea Challenger, Jim was pretty keen to get inside. He looked a bit concerned. You can see the equipment up around his knees. If I could quickly describe just what's inside the sub. As I mentioned, we're sort of sitting in this sort of position. Not sure it's going to handle it. And we've got a viewport down here. It's very hard to have a look at it. James Cameron, he did tell me that he did take the camera off a viewport, and he was able to contort his body to actually look out that viewport. But we relied on a very high quality camera, a 4K Red Epic, and that would give us a great vision on a monitor that was about here. We had a sonar monitor, screen from a sonar. We had another monitor over here for the boom camera and the auxiliary cameras. And also we had a monitor on this side, which was our sub-control system. We had a joystick for the pan tilt on one side, joystick for the pan tilt for the camera, a joystick for the pan tilt for the light. We had a joystick for the for driving the sub forward, aft. We had another lever control to maintain altitude. Yeah, so it was, when you're actually diving in the sub, there's a lot of things to think about. And if you're on an expedition with James Cameron, it's all about getting the shots. So, you know, focus, exposure comes before driving the sub. But of course, you've got to position the sub because that's also a mobile platform to get the shot. And I did give it a thumbs up. And the next day, it went for its initial dunking in Sydney Harbour in Garden Island, which is a naval dockyard. And it was actually on Australia Day 2012. And okay, we got the balance a little bit wrong, but pretty well it, you know, the weight and balance, it actually floated, it didn't sink to the bottom. So we were all pretty happy that day. The expedition then took off up to New Guinea. We had, it was pretty successful. We did a 1,000, 2,000, 4,000 and 8,000 metre dive almost consecutively with just 1-2 days between diving. For those interested, we actually had an acoustic comms and navigation system, and the navigation would work by transmitting a time of flight from a sub, and that would be received by transponders from a rigid hull inflatable boat, and another one from our main support ship, a ship called the Mermaid Sapphire. And by comparing the time of flight, the salinity of the water, salinity of the pressure, we could actually determine the horizontal distance, and we were able to calculate range rings, and intersecting range rings should theoretically be directly above the sub. And if you do enough points, particularly that there's a surface current and windage on the surface, that we were getting multiple points, and we were able to confirm the which intersect, this one rather than that one. Was the true intersect and the true location of Deep Sea Challenger. We also had voice and data comms, which was developed by L3 Oceana in West Australia, and it worked extremely well. Just some images before we finish up of a dive I did to 1,100 metres. There's obviously a vehicle that is filming Deep Sea Challenger, and those images are coming from a remotely operated vehicle that happened to come with the ship. But it was also our job to put a 3D camera system on it. This is pretty much your driving screen that you see in a sub. The Red Epic camera is the conic viewport is a 90-degree spherical sector window. It has a diopter to overcome the optical issue of going through a spherical sector window. Oh, lost it. Oh. Getting towards the end anyway, sorry, but it's a trap. Come on. Right, sorry. It's a spherical sector window, that's the image, and it'd be like driving a car with a camera on your bumper bar and looking at a TV screen. And I don't know, I just got pretty comfortable with it. Out in front is what we call a lander. It was other vehicles that we made, so we could deploy them on the bottom. They also had stills camera and also 3D imaging cameras. So we tried to cover the deployment of this vehicle so that we would have images of the vehicle on the bottom. And I was fortunate enough that I got to do this particular dive. Image from the ROV looking past the lander to the sub in the background. You can see the spotlight causing quite a large hotspot. Some of the LEDs, the brow LEDs operating. This is our forward-looking sonar, and also our large banks of LED arrays. And on the 26th of March in 2012, that's when James Cameron did his dive on Marianas Trench. This is fully deployed. Just to mention the steel shot weights that are released for the sub to ascend back to the surface. The batteries are all behind these polycarbonate covers, and you can see, if you look hard, all the Tygon tubing that's associated with them. This lighting arm is yet to be deployed, and that's done by the divers. And also there's a couple of stabilising fins on the bottom of the craft which helped keep its stability. The sub, when she's in the water, is in a vertical orientation, as you saw from the introduction slide. It is actually held on the surface by flotation because she's got those heavy weights on it. When those weights are released, the sub will accelerate to about 6 knots, but then she starts to pick up buoyancy. It actually gets lighter, and it will actually slow down of its own accord. If we didn't stop it with thrusters, it would probably hit the bottom at about 2.5 knots. The descent for 11,000 metres took approximately 2 hours. And I will admit, probably James was on the controls because he didn't want to crash land the sub. After the dive, he was pretty joyous. And that's my story. So.